everyone, we are the ocean temperature group. Actually, we added salinity to our group. I'm Ingrid.
I'm Alexa.
I'm Ahmet.
I'm Alex.
I'm Joey.
I'm Wenbo.
Okay, we focused our research on how do Argo flow data reflect changes in ocean temperature and salinity associated with the El Nino Southern oscillation cycle. First of all, Argo, what does Argo mean? Argo means Array for Real-Time Geostrophic Oceanography. And this map, it shows the different profiling float data carried out of Argo. And this second diagram shows the process, how Argo float is being deployed in the ocean. Then it goes down about like 2,000 meters in depth, and then it goes up again. And while ascending, it collects information on temperature and salinity, which is then transmitted to the satellite to different organizations.
Okay, so what is the El Nino Southern Oscillation Cycle? It's a climate phenomenon that occurs in the equatorial Pacific, and it's focused in these, it's divided into these established regions, 1, 2, 3, and 4. And the El Nino phase is when the surface temperatures in region 3 warm up, and La Nina is when they cool down. And this happens every few years, and it lasts for several months. And it's extremely unpredictable, and it has a lot of impacts on the climate, weather, and ocean processes.
So as we were talking about earlier, one of the big things that we focus on here is the thermocline. So as you can see, as we were saying, the thermocline is the difference between like warmer water on top and colder water on the bottom. It's just like a thinner layer, and it changes from El Nino to La Nina, and in the generally it's like it's between both of those, and just normally. So as we were focused on differences in thermocline across different positions, across different zones across the Pacific. And so, but we also, another thing we added was we're looking at something called the halocline, which is essentially a thermocline, but in regards to salinity. So you can see like what an average like profile of temperature and salinity would look like. So they both change at the halocline significantly. And this is kind of like what we investigated a lot of for the first part of our investigation. And another thing that we investigated, so we were also looking, because salinity is really dependent on how like the net gain or loss of water, so like evaporation and rain in like regions. So if it evaporates, the region become more saline. If it rains more, it'll become less saline. So that's especially relevant when you think about how like, so if it evaporates in one place and then moves to a different place and then rains there. Because there's different weather patterns associated with El Nino and La Nina. So with El Nino, water can evaporate from the middle of the ocean and then go to the edges and fall there. So we would expect to see more saline water like in the middle and less saline on the coast. And as opposed to La Nina, though, water tends to evaporate from the western Pacific, and then it would go up or go to eastern and then fall in the eastern Pacific. So essentially, that would change the salinity. So I'd make more saline in the western, less saline in the east. Oh, sorry,
That was not intentional.
And make more saline in the west, less saline in the east. Anyway, so you'd be able to see that in the salinity profile. So that's just just one of the things that we investigated. So at least for this, so the specific how we set this up for at least the first part is we look at the ONI. So ONI is essentially a measure of whether El Nino is happening or La Nina is happening. So it's like you can see El Nino red. You can see how it changes, and then 2 different years of which is happening. Specifically, we looked at we chose a specific month just because there's so much data. And we actually chose December to look at these because they have the most extreme values. And we set it up, we chose 2 seasons, 2 La Nina seasons, 2 La Nina seasons, and 2 neutral seasons in order to compare the temperature and salinity profiles in order to compare those and see how it can be measured.
So the 2 regions that we focused on there were 2 regions that most ocean aquifers focus on for El Nino. It's this area 3 and this area 4. We kind of modded area 4 to fit best in our better interests, because in area 3 it really measures the temperature on the surface very well. But on area 4, we mod it so that it really gets that thermocline, so we can actually see the curve going down. Yeah. So these are the average temperatures in the regions 3 and 4. So this one is the pressure that as it goes down. We can technically assume that for every one pressure that increases, the depth that decreases by 1 meter. And these different curves, like you can see, the red ones for El Nino, the blue ones for La Nina, and then the green ones for neutral. And you can actually see here that the surface temperature is different for each of them. El Nino is a bit more hotter than La Nina, and neutral is right in the middle. But in area 4, it was easier to see actually the thermoclines and how each of them are kind of named differently. For El Nino, it's kind of more straightforward, and for in the neutral, it's in the middle, and for La Nina, it's more sloped downwards. These are just the average temperature profiles, including the variability. The lines that are between the two, the mean line is the line that for the 90th variability band. And like you can, something that's interesting and what we wish we could have researched more was that why is El Nino have a smaller band than the rest of them. We did the same thing for the average salinity. So for each profile, we took the approximate for each profile. We fixed the pressure, and we took the average salinity of each of them. For area 3, it was a bit more confusing to see what was going on, but because we modded area 4, it was more easier to see that actually El Nino on the surface was less salinic than La Nina. And we also did the same thing for the average variability. And for this one, like this, it happens the same phenomenon that El Nino does have a smaller variability than the rest of them.
Okay, so we have these temperature depth profile curves where as you go down in the ocean, your temperature gets colder, right? And so we know that these profiles change with El Nino and La Nina, and the question is, are there kind of some underlying profile curves that we can pull out of these? And so one way that we can do this is with functional principal components analysis. So this is, if you've seen principal components analysis before, it's basically the same idea, except we're going to deal with curves instead of vectors. So what we do is we say each one of these temperature profiles, we're going to assume that it's a linear combination of some kind of principal curves, and then we're going to find these components that maximize that kind of explained variability. So we fit those to the temperature profiles in El Nino region 3. And this is what we get. So we get these 8 eigenfunctions, which represent the kind of primary modes of variation in the temperature profiles. So here the dashed line represents the mean profile, and eigenfunctions 1 and 2 explain most of the variance here. So we can see if you kind of take these blue lines and we add them to the mean, so that the dashed line here in each of these plots is the mean, and then the blue line is the mean plus or minus the eigenfunction. So you can construct a profile by taking the mean and adding linear combinations of these eigenfunctions. So on the right side here, the green is the mean profile, and then you can add PC1, and then you can add some PC2, and then you can get these different profiles, right? So anyway, we can do that, and then each of our curves that we have, we can represent as a linear combination of these principal profiles. And we can think about the coefficients for these linear combinations, and that's what we look at next. So it turns out that looking at PC1 and PC2, we get this kind of banana shape. And over on the left-hand side, the ONI, so the ONI again is this measure of El Nino. So when El Nino is happening, you have ONI close to 2, and when La Nina is happening, it's at -1. So on the left side, we have La Nina, and on the right side, we have El Nino. So what this kind of means is that there's some kind of space of curves, and as you move along that space, you're approximately going from El Nino to La Nina. We can actually visualize this, so there's this line along this kind of low-dimensional space where all of our curves live, and we can move along it and see what that looks like. And so this is what that looks like. So on the bottom right here, we have a representation of where we are in PCA loading space. And then the main plot here is the actual profile. So on the far right-hand side, we can see El Nino, which is when we have warm water that comes deeper. And on the left side, we have La Nina, where we have mostly cold water that comes up close to the surface, right?
So we have looked at depth a lot in comparison to temperature and salinity. So what's going on at the surface? Well, so we focused on the surface for identifying signals for El Nino. And so shown in this image is for the anomalies for January. It's the month right after the very strong El Nino. And so you can see here this anomaly that is controlled for mean but not for seasonality. So you can see some seasonal patterns, but this is basically what we want to do. So here I basically found the average anomalies having focused on fixing the mean and seasonality patterns. And so this is over 12 months for 10 years, so 120 areas. And so I found areas for subsets of 3 in the equatorial Pacific. And so you can see here, you can see a certain pattern for this year 2016. So by interpolating for spaces, we use thin plane splines. So it's a non-parametric spline function, f of x, which minimalizes penalized sum of squares. So in this case, we want to minimize the sum of squares and the penalty term, which includes smoothness, lambda. And we find the smoothness lambda by this equation, which is a generalized cross-validation function. And so through this, we can control the smoothness and the least squares residuals for non-parametric function. So by having this process for 3 different subsets, I made some time series models. And so we want to find the areas where there's the strongest signal. So we use this correlation plot to find the strongest signal. And we found the strongest signal as shown in the literature. We found further evidence for this in salinity area 4 and temperature area 3. You can see there's a sort of an inverse relationship, and this is supported by the 0.73 correlation value. And so we wanted to work with this time series. So what do we do with it? Well, first we want to make sure that we can actually make a model out of it. But then in order to make a model out of it, we need to see if there's actually correlation between different lag values. And so if there is correlation between different lag values, we can make a model. And because we see a sort of dependency on different lags, so as you can see here in this alternating correlation plot, you see anomaly for temperature salinity for correlation 1 is onto itself. The other decrease in correlations is for increasing lag terms. And so here we have the ACF and PACF charts for salinity and temperature at the strongest signal point. And so you can see here that we have AR1 using this graph, but then when I use AutoFit in R, the best model is actually ARMA 3.2 for temperature, for example. But then because this is not parsimonious, it makes not much physical sense, because each month's values will depend most strongly on the previous months, and even weaker for months before that. So this makes physical sense. And so you can see here, the top one is for salinity and the bottom one is for temperature, and we see it through the similarity with the first time lag correlation. It's very similar. And so we can say that for this, the month correlates with the previous month, and ZT is the additional weather, the additional natural events.
Some of the takeaways that we got from the project was that Argo profiles actually reflect the ocean temperature and salinity during the end cycle.
We also found that these temperature profiles have a nice low-dimensional structure that changes nicely with El Nino and La Nina.
And then we were actually successful in seeing how salinity profile has changed between La Nina, El Nino, and neutral. And we thought that was pretty interesting because we can actually see the changes related to rainfall and changing weather patterns. We actually see those in salinity profiles.
And we also seen an inverse relationship between area 4's salinity and area 3's temperature.
So an area for future work would be to create a predictive model for the end cell because of its large impacts on like climate and weather, and we would use some of the signs that we already know and incorporate them into a model, and also to delve further into the relationship between temperature and salinity during the end cell cycle.
This, as well as we can also include maybe more, like such as along with temperature salinity, we can see other variables that might also influence this pattern.
I think that's it.
Any questions? Oh, Chris?
So could you go back to one of your slides where you showed the profiles? And you're saying these two are El Nino and these are La Nina and stuff?
Yes, the salinity profiles.
Yeah, so how many Argo floats do you have, say, going into one of those profiles? Is that one Argo float?
No, it's a lot. I'd say like 200.
No, it's 2,000.
Well, 200 per region. Right. Oh, yeah, okay. Well, there's 200 like floats, but then I think they're over. How much are in the region?
Okay,
Like, can you get to a
so
map?
there's 2,000 in these. This is 2,000,
Oh,
and then if you go to this is 22,000 total to estimate here.
Can you get to the map?
So that curve you're
Yeah.
showing is kind of an average?
Yeah, the average.
And then this color coding here is determined by the ONI?
Yeah, it's just
kind of windows of ONI that say this is El Nino and this is.
Because we chose two seasons for each type.
And 6 years of data, is that?
Sorry, so what's the so take the two El Nino ones here on the right in area 3. What's the difference between those two curves?
They're different years, and they have different El Nino values, like the ONI values.
So these are both similar profiles during specific years, but those are El Nino years.
Okay, so one of them is in this particular area you're averaging over all the floats in area 3 in December. Okay.
You had to list them on the previous slide, I think. Yeah, this one.
Yeah, so for El Nino, it will be 2014 and 2015.
Yeah.
Not just like I think I missed this slide where you said temperature and rainfall were the ones which affected.
That affected. Well, it's kind of complicated. So El Nino itself is caused by warming in the Western Pacific. So there is some not difficulty, but it's hard to say what causes which, because I mean it is inherently affected by warming the oceans. And
like you had those graphs where I think she was showing some. So was it like you're finding your best positive was that a casual a relationship that you were trying to find, or was it?
you guys can say what you guys think. I would say a bigger focus of our project was I think on our title slide we had the question that we were trying to specifically see if we could see what we thought would happen in the Argo flow data and see if we could actually.
The relationship that you were trying to establish.
No.
With those.
Yeah. I mean, there are causes, but we're trying to confirm those causes. We thought some of our salinity changes are caused by changing weather patterns, but those changing weather patterns are in turn caused by just naturally warming waters. So we were trying to really establish cause.
Okay, so that's when your final slides, you just had that it was consistent with your, I think one of your final slides mentioned.
Yes, so we did see differences in region and temperature. We saw thermoclimate changing in different regions, which we thought would happen. We saw salinity was changing because of the changing weather patterns. So we were able to see some of those things that we thought we would see.
Yeah.
This might be an off-tangent question, but what if there was an oil spill in the ocean? So how that will affect everything?
So this is very similar to what I mentioned because we only looked at salinity and temperature.
Uh-huh.
So if we were to continue with more research in this subject, we would include more variables such as maybe like natural disasters or maybe some oil spills as you mentioned. So that would be an interesting topic.
Okay. So let's say like oil spills, tsunamis, even earthquakes within like the ocean, that would just change, everything what you guys did.
Not
Pretty much.
probably not that drastic. It's a very small area, but we can hopefully research more. But.
The oil spill in particular may be too small
Okay.
to really affect
Really
these
affect
these large things.
Okay.
But maybe something like hurricanes
Yeah.
or they're called typhoons in the Pacific. So. Anything else? Well, let's thank the team again.